Okay, I say this to you not to scare you, but just to prepare you. This unit, which deals with exponential and logarithmic functions, some people find quite challenging. So I'm not saying you're going to find it challenging. I'm telling you that so that hopefully we can avoid that pitfall, that general difficulty or anxiety associated with this unit by, as soon as you encountering something you don't understand, asking about it or clarifying it. Okay. Like trigonometry, there can be some misconceptions in this unit. By the way, speaking of the trigonometry exam, I'm fairly happy with the results. I think a few of you could do better. When we get a chance to go over the exam, I would encourage some of you to do a rewrite, because I think you're more capable than what some of the marks reflected. Anyway, this is Unit 5. It deals with exponential and logarithmic functions. Logarithms are a mathematical invention created by a fellow by the name of John Napier in the 1600s. And they didn't have electricity back then or any kind of technology like that. But John Napier invented what's called the slide rule. And a slide rule, if you know what you're doing with a slide rule, you can do any calculations you want with a slide rule. So what a slide rule consists of, it uses logarithms, by the way. And I'm just showing you this as a point of interest to you. This isn't something we need to learn how to use. It contains two pieces of, usually they're made out of bamboo, because bamboo doesn't warp in the moisture. And they have, I don't know how this works. Okay, I've taught myself how to do some really fundamental things like multiply using this. But you can, and then there's another thing that slides around, and it's got a line on it that they actually called the cursor. That line on it is called the cursor, even back in the 1600s. And using this, you can do pretty much any calculation that you could do on your graphing calculator. You could find the value of square roots, cube roots, fourth roots. You can, if you want to know the sine of pi over 32 radians, you could use this thing to do it. These went out of fashion probably in the mid-70s when pocket calculators became cheaper. They were still pretty expensive. If back in like the 60s and 50s, if you were really cool, you carried a little pocket slide rule with you. So they made these things really big and really small. They made circular ones. But seriously, you can do all kinds of calculations on this thing. And it's because of what's called a logarithm, this invention of John Napier's. So what we're going to do in this unit is we're going to be looking at exponential functions, and we're going to be analyzing them in detail. And this will include the graphs of basic exponential functions, transformations of exponential functions, and solving exponential equations, as well as doing some applications along the way. Then what we're going to do is we're going to repeat the whole process with logarithms. So when we learn about basic exponential functions as graphs, we're going to learn about basic logarithmic functions as graphs. When we learn about transformations of exponential functions, we're going to do the same thing with transformations of logarithmic functions. And we're going to be solving logarithmic equations. And wedged in between there, in order for us to solve logarithmic equations, we need to know how to apply what are called the laws of logarithms. So we're going to start off today. I think this must be page 1, obviously, of your unit handout. It's the very first lesson. We're going to be looking at very basic exponential functions and solving problems that involve two types of exponential change, growth and decay. And if you're really on top of things in your mind, you will see a very close connection between what we're doing today and what you did in Math 20-1 with geometric series and sequences. Okay. All right. So what is an exponential function? An exponential function, and I'm not using function notation here, I'm just using the y and x, is any function that can be written as y equals some number raised to a power of x or a variation of it. Obviously, if we transform that function, y equals c to the x, then you get another exponential function. I think that would be obvious. Look what it says about c, and I want to break this down here. The base c must be greater than 0. So that's telling you two things, as well as being greater than 0. It's telling you very specifically it can't be 0, and it can't be negative. But it also says that c is not allowed to be 1. So why is c not allowed to be 0? Well, if c is 0, then you would have this as a function, and 0 to anything other than 0 is 0, and this is not an exponential function. It's a polynomial function of degree 0. It's a constant function. If the base was 1, then you would have 1 to the x, but 1 to any power is always 1. So you're left with, again, a constant polynomial function. That's not exponential. So the base, and I don't want to get into negative in detail, but if you had a negative base, that creates problems because negative bases raised to even exponents become positive, and negative bases raised to odd exponents become negative. And it becomes particularly troublesome because if the exponent x happens to be a half, then that's a square root and it wouldn't exist. But if it happens to be a third, that's a cube root, and you can take the cube root of a negative. It causes all kinds of problems. So what we say is we never want a base that's negative in high school. So visually what this means is if you look at a number line that represents the base c, you're not allowed to have a base of 0, and you're not allowed to have a base of 1. And I would like you to write this little diagram down in your notes because we're going to be adding to it to help you understand different types of exponential functions. So you want to write it someplace where you're going to have enough room to write a couple of words above it in different places. I mean, you don't have to, but I think it's going to be helpful. And I actually thought that I had included that diagram in your notes, but I was mistaken. So what are some examples of exponential functions? Anything where you have a number raised to a variable. So f of x equals 1.35 raised to the x would be an exponential function. Don't forget that f of x is just a fancy way of writing y. There's more to it than that. Otherwise, we would just write y. But in its simplest explanation, that's what f of x is. Y equals 2 to the x is a very basic exponential function. N of t, which means the variable n is a function of t, n is equal to 1/2 raised to the t. So it doesn't have to be x, obviously. It could be any variables you want. So for example 1, we want to sketch a graph of each exponential function without using a graphing calculator. We need to learn about, how can I put this? We need to learn about the behavior of an exponential function based on the value of c. The goal after this example is for you to look at any c value in an exponential function and tell me what the graph is doing. So after we graph it, we want to find the domain, range, x and y intercepts if there are any, whether the graph represents an increasing or a decreasing function, and we also want the equation of something called a horizontal asymptote. So the first one is 4 to the x. Y equals 4 to the x. And I've got a little table of values for us to complete to learn from. If I were to figure out what 4 to the 0 is, I would get 1. So, maybe I will write this here. This is 4 to the 0, so the y coordinate is 1. If I were to use x equals 1, I would have 4 raised to the power of 1, which is 4, and 4 raised to the 2 is 16. And what I want you to notice, this is one of the major parts of this example, is that as x goes up by 1, y gets quadrupled, which means multiplied by 4. So we're going up by 1 in each of these for x. And what's happening to y is it's being multiplied by the base of 4. And if you dissect the meaning of 4 to the x, that should make sense, because if you have one more value in the exponent, you're multiplying by an extra 4 each time. What that means, by the way, is that if you were to go backwards from here to here, you would have to divide by 4. from here to here, you would have to divide by 4. So, you know, what is 4 to the negative 1? Well, if you go back to Math 9 or 10, maybe 10, I don't think you do negative exponents in Math 9. So in grade 10, you're taught the meaning of a negative exponent. Thank you, Mr. Hetlinger. And a negative exponent simply means the reciprocal of the same thing written with the positive exponent. So what 4 to the negative 1 is 1 over 4 to the positive 1, which is a quarter. But I want you to notice that we could have arrived at that by simply taking the y coordinate when x is 0 and dividing by 4. So if x goes up by 1, y gets multiplied by 4. If x decreases by 1, y would be divided by 4, which means if we take a quarter divided by 4, we'll get a 16th here. And you know, the Math 10 approach is to say 4 to the negative 2 is 1 over 4 to the positive 2, which is 1/16. You notice, by the way, and I've cluttered this up with a lot of, that's no good. I've cluttered this up with a lot of extra material, but what I want us to focus on, give me a second, please. Okay, I lost the setting. I won't worry about it. I'll just risk using the highlighter here. What we want to focus on is that these are the y coordinates. Right, it goes from 1/16 to 1/4 to 1 to 4 to 16. I also want you to focus on the fact that when x is 0, you're going to have a y-intercept of 1, because 4 to the 0 is 1. So when we plot this, we can plot a point on the y-axis at 1. And then I want to make sure about something. Is your grid scaled the same way my grid is? Okay, so be careful with that. Sometimes the diploma exam will do that, and you want to be very cautious. I've been caught with that where I look over at 1 square, and I think that's 1. But in this case, every 2 squares is 1. The important thing you learn from this table is that when you increase x by 1, y gets multiplied by 4, so it goes from 1 to 4. When we increase x by 1 again, 4 gets multiplied by 4, and you get 16. Now, we have a problem when we go in the opposite direction, and that's that when I look at negative 1, the y-coordinate is a quarter, and that's getting pretty close to the x-axis, isn't it? Like, to draw it, especially with me, I'm drawing this big blobby dot. Now, do I even want to draw 1/16? I don't think I can. And I'm not sure that you can or you want to, but I want to make a point. If we keep dividing by 4 every time we go in this direction, then that means we will always get some y-coordinate. We will never reach 0. If I were to look at x equals, and we can do this on the calculator, negative 10, well, I'll do it up here. If x was negative 10, then y would be 4 to the negative 10, which is 1 over 4 to the 10, and I don't even want to think about what 4 to the 10 is. It's a big number. You can calculate it if you want, but 1 divided by that big number, no matter how big that number is, you will never reach 0. It just gets smaller and smaller and smaller. And for that reason, when you sketch this graph, wait to see what I draw before you start drawing things. When you sketch this graph, it's probably best to just end it there. And how do we indicate visually that that graph is going down? This is a weird thing mathematically. That graph is going down forever, but it never reaches the x-axis. Do you know, Farhan? Right, you draw a horizontal asymptote. And that's indicated by a dotted line. And that's what the graph looks like. This is what 4 to the x looks like. It increases more rapidly the further you go. It's not like a parabola that just keeps getting bigger and bigger. It gets bigger and bigger by a bigger and bigger amount all the time. I don't know if you remember in Math 20, but I gave you an example when we were talking about geometric sequences of taking a penny and doubling it each day for 30 days. Do you remember that? It's hard to imagine, but if you haven't heard this before, you can try this with your parents or your brother or your sister or your friend. Tell them that, you want them to give you a penny on the first day of October, and 2 pennies on the second, and 4 on the third, and 8. In other words, you're going to be looking at this pattern. It's doubling every day. By the time you get to the 31st day, I believe on the 31st day alone, you have over $10.7 million. It's hard to imagine that just doubling 31 times happens. And I can see some of you are trying to figure that out now. So if we go, and by the way, it's a lot easier to use with this rather than geometric formulas from Math 20. A lot easier. Because in geometric, you have that n-1 thing, which is goofy. On the 31st day, actually, on the 30th day, you have $10.7 million. On the 31st day, you have, actually, this would be the 32nd day. We do have to deal with that -1 someplace. But it grows phenomenally rapidly. Okay, let's answer the questions now. What is the domain? Well, the domain is any real number. If you look at the function as an equation, we can figure out that x can be any real number because you're allowed to take 4 raised to anything. 4 to negatives, 4 to positives, 4 to 0. But if you look at the graph, you can see that the graph goes to the left forever. And although it's quite steep on the right-hand side, it is always moving to the right forever, just going up a lot as it moves to the right. The range is y is greater than 0. Not y is greater than or equal to 0, like, say, a parabola whose vertex is at the origin, but y is greater than 0 because it's always above that asymptote. How close can it get to 0? No matter how close you visualize it being to 0, it can get closer. It can get like infinitely close to 0. X-intercept, well, if it never touches the x-axis, there is no x-intercept. Y-intercept is y equals 1 or 0, 1 if you want to use an ordered pair. And the horizontal asymptote is the x-axis, whose equation is y equals 0. We're good with that? Any questions with example 1a? All right. What about if we have 1/2 to the x? So this is 1b. Well, let's start with x equals 0. And what I'm doing is I'm putting the x coordinate into the function. So I'm not going to write out all my substitutions, but let's start with x equals 0. When I take 1/2 or 0.5 raised to the 0, I get 1. What does that tell us? It tells us that this graph also has a y-intercept of 1. Is your grid scaled the same as mine horizontally? I just wanted to make sure. If I were to look at x equals 1, I would take 1/2 raised to the 1, and that would give me 1/2. If I were to take 1/2 and square it, this one I will write down, y equals 1/2 to the 2 means I have to square the 1 in the numerator to get 1. I have to square the 2 in the denominator to get 4, so I get 1/4. But what's happening is we're multiplying by a half. So I'm about to take a leap here in my explanations and say what the base of an exponential function is the number that y gets multiplied by regularly. So when the base was 4, y was being quadrupled regularly. It was being multiplied by 4. When the base is 1/2, y is being multiplied by a half regularly, which means, everybody, that if you go in the opposite direction, you would be dividing by a half, which is the same as doubling. So if you're going on this table down to larger x's, you're basically dividing by 2 each time, which means you're doing the opposite and you're multiplying by 2 as you go in the other direction. And, just to pick a number here, let's take this one just to demonstrate why we get 8. It's 1/2 raised to the negative 3. But you're taught in grade 10 that a negative exponent, as well as meaning 1 over, means the reciprocal raised to a positive exponent. So this is equal to 2 over 1 cubed. Well, 2 cubed is 8, 1 cubed is 1, so it's 8 over 1. And we can plot the points now. When x is 1, y is a half. Now we're running into the same problem we had with the previous question on the left-hand side of the graph, which is that the next point is at a quarter, which I suppose I can put a quarter in there, right? Roughly. But it's going to keep getting smaller. The next one is going to be an 1/8. And then if I add 1 to x again, it's going to be a 1/16, which gets pretty difficult to plot. When x was -1, it's 2. When x is -2, it's 4. I mean, I'm not even looking at the table of values anymore. I'm just using the pattern, which is going left to right, y gets cut in half. Going right to left, y gets doubled. So it looks like the following. Got our asymptote. What is the domain? The domain is x is any real number. The range is still y is greater than 0. I hope you would see that I don't, in terms of transformations, everybody, stretching, reflecting, shifting, you can never alter the domain of this. It's going to go left and right forever no matter what you do. The range can be affected, though, if you were to shift this graph down or up. That would move the asymptote. X-intercept, there still is none. Y-intercept is still y equals 1, or in ordered pair form, 0, 1, and the horizontal asymptote is y equals 0. Now, I didn't address something, and I don't know if I have it here, but you were also asked in question 1 for A and B to say whether the thing is increasing or decreasing. And the function, what you need to remember is in the context of graphs, increasing and decreasing refers to left to right. Always from left to right. So when you take a look at the first graph, which is this one, if I were walking along that line like it's a hill, and I were walking left to right, my height above the ground is going to be increasing. So y is increasing as x increases. And that means that this is called an increasing function. I think it's obvious, but I'm just going to point it out, and I hope it's obvious to you when I point it out. The reason it's increasing is because the base is greater than 1. The base is 4. So things get multiplied by 4 regularly as we go left to right, which means things get bigger. It increases. Whereas when we take a look at this next graph for B, this is a decreasing exponential function. And the fundamental reason for it, or the telltale sign, is that the base is smaller than 1. Because if you multiply y by a number less than 1, then y starts getting smaller. So increasing functions, and this is in your handout, this picture, of the form y equals c to the x, where c is greater than 1. That's an increasing function. They look like this. This diagram doesn't have an asymptote on it, but it could. And decreasing have a c value between 0 and 1. And if we go back to that diagram that I asked you to write, we could add another layer of information to this, and we could say, well, when the base is between 0 and 1, you're talking about a decreasing function, and when the base is greater than 1, you're talking about an increasing function. Okay? Not everybody needs this diagram, but some people are very visual and they want some kind of mathematical diagram to look at. This is a line diagram. It's brilliant. It tells you exactly what you need to know mathematically. Rather than me saying, 0 is less than c, which is less than 1, this just shows me exactly what I'm talking about between 0 and 1. All right, what function of the form y equals c to the x does this graph represent? Well, what you need to do, it's a very simple question, is you need to determine what number y is being multiplied by regularly as you go left to right. We can see it's a decreasing function, so the number has to be less than 1. If you were to, I know most people don't need a table of values here, but we go from -2 comma 16, we increase x by 1, and the y coordinate becomes 4. To go from -2 to -1 is an increase of 1. We're going 1 to the right. And y goes from 16 to 4, which means that the base is 1/4. We're multiplying things by a quarter. So the equation of this function is 1/4 in brackets raised to the x. Could you write 0.25 to the x without brackets? Sure. Could you write, because you're going to be clever about it, 4 to the negative x? Of course. Because 4 to the negative x means 1 over 4 to the positive x. So now I'm going to introduce 2 other words. If you have an increasing exponential function, which is what I have up here, it says c is greater than 1. That's an increasing. You will often see, instead of the word increasing, you will see the phrase exponential growth. Okay? So the example of me doubling that amount of money regularly is an example of exponential growth. What are some examples of exponential growth? Investments. Hopefully when you invest your money, it's exponential growth. It's not exponential decline. You don't want that with your investment. If I had a rare coin, it's going to grow exponentially. Populations of bacteria grow exponentially. And by the way, if you know something about how bacteria multiply, they multiply by the process of biological fission, where cells split. So one bacteria becomes 2, 2 become 4, 4 becomes 8. Well, that would be y equals 2 to the x, because it's doubling. Populations of people as well. Although people don't split, they grow exponentially for other reasons. If you have a function that is decreasing or declining, we call that exponential decay. So you're going to see that word. Examples of exponential decay would be if I buy a new vehicle. Every year that I drive that vehicle, it becomes less and less and less and less valuable. Eventually, what's going to happen if I take care of it is it's going to become an antique, and it will enter into an exponential growth in terms of its value. Radioactive decay, which if you take Physics 30, we will learn a lot about, and we'll look at a couple of examples of that in this course as well. So I guess you could add to that diagram now, instead of saying just between 0 and 1 for the base, it's a decreasing function. You could say, well, it's exponential decay. And you could say it's exponential growth if c is greater than 1. And again, I'm just, I'm kind of approaching this at a lot of different angles so that you understand that we have different ways to describe what's going on. We can talk about the value of the base, we can talk about what's happening to the graph, or we can talk about what's the real life application of it, growth or decay. Does anybody have any questions about this diagram or anything we've covered so far? All right, I think we just have a couple of examples. Now we got a problem here. I don't know. I wish everybody would have a big meeting and make a decision. The text uses C for the base, but the formula sheet uses B for the base. And I understand why the textbook uses C. It's because when we do transformations, there is a parameter labeled C, isn't there? This is going to be something we're going to have to wrap our heads around, because when you look at your formula sheet, not that there's any real valuable information there yet. But I will show it to you in a second, because I notice a lot of you looking. We use B for the base, but we also use B on the formula sheet for a parameter that deals with a horizontal stretch or reflection. Let me show you on your formula sheet where this appears. Now, it doesn't really appear as y equals b to the x. There's more to it. Here's a growth and decay formula that we're going to talk about a little bit next week. Y equals a multiplied by b to the t over p. And if we were to water this formula on your formula sheet down so that there is no vertical stretch. If there's no vertical stretch, then this number is out of the game. And we won't worry about the fact that it's P. If there's no horizontal stretch, the variable t is not being multiplied by anything. And by the way, the variable t in that formula that's on your formula sheet is being multiplied by 1 over p, because it's written as over p. This is what we've been talking about in this lesson. Y equals c to the x. Except that all of the applications, maybe I should say, most of the applications of growth and decay we look at, it will be time, not x. What's my investment after 20 years? What's that mint condition Mad magazine from 1972 worth in 30 years? How much is my car worth 20 months later? We're always going to be measuring things with respect to time. All right, let's take a look at example 3. A radioactive sample of radium. Radium-225 is just it's an isotope. I mean, you've all taken Science 10. You understand a little bit about chemistry. Different atoms have different isotopes. So when you look at radium on the periodic table, radium is defined by having, and I got to find it. It doesn't matter. I'm not teaching a science class here. But radium is defined by having 88 protons in the nucleus. Okay? Well, some radium nuclei have 88 protons, and they have maybe 140 neutrons, and some have 141 neutrons. Depending on the number of neutrons, you have these different types of radium. Don't be confused by this Ra-225. It's the name of this stuff. It's the isotope of radium. And it has a half-life of 15 days. What that means, shouldn't have done that. What that means when we say the half-life is 15 days is every 15 days you're going to have half as much remaining as you had at the beginning of the 15 days. And you can even see that by looking at the graph. Because if you look at the amount of radium present to begin with, it's 1 gram, which is very contrived. We're going to have to eventually deal with the fact that that y-intercept is not always 1. But it's 1 gram. And 1 15-day interval later, so this x-coordinate is 1, but it represents 15 days. You can see that after 15 days, the y coordinate, which is the amount remaining or the mass remaining, is half. It used to be the case that Alberta education would always put some explanation of half-life into exam problems, and they don't necessarily do that anymore. And what that means, unfortunately, is even if you don't take physics, and we will learn in detail about half-life in physics, you will just be told that. And you're expected to know what it means. All right, let's take a look at the questions. What is the initial mass? Well, initial mass is the mass at t equals 0. Initial means at the beginning. And what this is asking you to do is look at the y-intercept. It's 1.0 grams. It's how much we have at the very beginning. What value does the mass approach as time passes? So I'm going to write this in a different way just for my calculus students because you're going to see this notation a lot. The second part of this question says, as t gets big, what happens to the mass? That's just another way of saying that second part of the question. What will the mass approach as time goes on? Well, it's going to approach 0. And the reason it's going to approach 0 is because this is a math class. And in the math class, we say there's a horizontal asymptote there. Okay. So as the time elapses, the mass approaches 0 grams. Now, I laughed and said, because this is a math class, for the following reason. In physics, I'm going to tell you, yes, it will reach 0 eventually. And I want to talk about this, because the reality of it is, sooner or later, you'll be down to one atom of radium-225, and it will decay. It will change into something else. So we have a bit of a problem here, and Alberta Ed hasn't really sorted this out. Mathematically, it approaches 0 and never reaches 0, but physically, it does reach 0. It's going to reach 0 at some point. And I don't know that you'll ever have to worry about that, but I want to cover my tracks here and make sure that I got it. Okay. What else are we asked here? What are the domain and range? Well, I told you before that the domain of y equals c to the x is any real number, but this is not any real number in this case because it has a real life meaning to the variables. X, which is time, relates to the domain, and when you take a look at this, the domain is that number, is that expression rather. T is greater than or equal to 0. Can we talk about this graph existing when t is 0? Sure. Can we talk about the graph existing when t is positive? 2 minutes, 2 days, 2 years? Yes. But we can't talk about negative. We don't like to talk about negative time. What about the range? Well, the range doesn't go up forever. It starts here at 1 and goes down, which means that the range, which is the mass, is between 1.0 and 0, and it can equal 1.0. So the mass could be 1.0, or it could be anything less than 1.0, up to but not including 0, mathematically. Sometimes what you need to do is you need to look at the real situation and figure out whether your domain and range change from what they would be if it was just a y and x thing. Any questions with B? All right, write the exponential decay model that relates the mass. Well, this matches perfectly with what we've been talking about, which is y equals c to the x, where c is the multiplication factor that happens regularly. It's 1/2 to the x, except its mass equals 1/2, and I'm going to just use 0.5, raised to the t. Now, you want to be careful here. T is not actually time, is it? Well, it's not time in days. It's 15-day intervals. So when t is 2, it's 30 days. You don't know how to handle this if we put days yet. We're going to learn that tomorrow. Well, not tomorrow. Tomorrow we're going to be sleeping in. We're going to learn that on Monday. How many days would it take to decay to 0.023? Well, holy smokes. I don't think we can read that graph, can we? I'm not comfortable. I mean, 0.023, there's 0.1. This would be 0.01, 0.02. Like, I mean, it's someplace there. I don't think I could read it very well. Yep. Does yours have a different number?
To decay to 1/30th.
To 1/30th. Okay. Thank you. Of the original mass. Uh, 1/30 is 0.03 repeating, is it? Can you verify that? Thank you. Sorry about that. So, could I try to estimate where that is? I could, but I'm not comfortable doing it on paper. So I suppose what I could do, since I know mass is 0.5 to the t, I could put 0.03 repeating here and solve this for t. The problem is you don't know how to solve that for t. You know what you need to know how to solve, you know what you need to be taught before you can learn how to solve that for t? Logarithms. That's the use of logarithms here. So we're going to have to solve this graphically on our calculator. We are going to be graphing this function of 0.5 raised to the x. I might as well set up my window setting right now. I'm going to set it up to kind of match this. I'm going to go from 0 to, I'm going to go up to 15 because I don't know exactly where these two are going to intersect. They might intersect further to the right. You can always adjust it later. In fact, I'm going to put this at 6 just for now to show you what I'm talking about. My y, I'm going to go negative 0.5 to 1. I want to see this graph starting up at 1, but I don't want to just end my view right at the bottom of my screen. I want to be able to see a little bit below the axis, that's all. And I'm also going to graph y equals 1/30, because 1/30th of the original mass is 1/30th of a gram because the original mass was a gram. And now what happens when I graph it? There's my nice graph, looks good. There's 0.03 repeating. Now, I think I see the point of intersection. I think I do. But if I didn't, then I would increase my x coordinate in my x max window setting feature. I'm going to find the point of intersection here by going to my calculate menu and choosing intersect. The nice thing about having only two functions visible or entered is all you have to do is hit enter 3 times and your calculator does the work, as long as the point of intersection is there, and it is. So the value of x that produces 1/30th of the original mass is 4.9 is 4.9. That's not days. That's 4.9 15-day intervals. So we still need to take 4.9 and multiply by 15 days per interval, and we're going to get very close to 75. But I'm going to quit out of here, pull up my x value that's currently stored, and multiply by 15. So the answer is 74 days to the nearest day. Any questions with that example? I think that's the last part of this example, yeah. Any questions with that example? Did I say 74? All right, we have one more to go, and this will actually be something that I can, even though it's not quite in your notes yet, I can use to teach you about this y equals a times b to the t over p. A little bit. You'll start to see when we're done with this example what the a does. We have two towns. We have Allentown and Brementown. Allentown currently has a population of 75,000, and they don't like what's going on. Is that my phone? Thank you, Mr. Hetlinger. They don't like what's going on. Politics, whatever, taxes are too high. People are leaving. And as a result of that, the population is decreasing at a rate of 5% per annum. Annum means year. Annum is, I believe, a Latin word that we get the word annual from. So when you say per annum, you mean per year. Brementown, man, they've got free coffee and donut days on the weekends. They've got parades. Everything's beautiful there. And their population is increasing at a rate of 9% per annum. You'll notice that I put /a instead of writing per annum. And by the way, a is the symbol we use for years. So on a math exam, if you wanted to write 10 years, you'd write 10a. What are the exponential functions for each of the towns? Now, I just want to begin with here, do a rough sketch of these. Is it the case that Allentown is decreasing? And it's decreasing at 5%? 5%. So you can choose to sketch these or not. It's not really important. But this is what the graph for Allentown is going to look like. The only problem is this is not 1, is it? It's 75,000. Because that's the original population. That's the population as of now, which is t equals 0. So this is 75,000. And when you take a look at Brementown, Brementown has a current population of, I think I saw 100,000, 10,000, and it's increasing. Now, I'm not so sure that this is intuitively obvious to everybody, but take a look at the rate of change of the populations. Allentown is losing 5% every year. Brementown is gaining 9% every year. So to me, it's kind of intuitively obvious that Brementown increases at a greater rate than Allentown decreases. In other words, if I drew it like this, I don't think I would be doing it justice. It has to be kind of steeper than the negative steepness of Allentown, because it's going up at a greater rate. And I don't know exactly. This is the steepness doesn't matter. I'm just trying to be a little bit precise here. So if we go from y equals, and I'm going to use b for a base, b to the x, having a y-intercept of 1, then what could I do to, and don't draw this, but here's 1. It's not even accurate. There's b to the x, which has a y-intercept of 1. What could I do to that graph to simply draw that y-intercept up to 75,000? The answer is I would multiply the function by 75,000. I could stretch it vertically by a factor of 75,000. And this means that the population function here will be equal to 75,000 times some base raised to the number of years. I could use t. I'm going to use n for number of years. We'll fill in the base in a second, but I want you to understand that on your formula sheet where you see this a, this is always the original amount. original value of the car, original number of bacteria in the petri dish, original mass of radioactive isotope, original number of people in Allentown. What that means for Brementown is the formula for the population function for Brementown would be 10,000 times the base, which I still have to discuss with you, raised to the number of years. We go through this calculation that I'm going to talk about right now as a detour in Math 20. The example that I have in one of my problems that we do in Math 20 is we have shingles. Well, we don't have shingles. We don't have the disease shingles. We have shingles on a roof. They're brand new shingles. And they lose, well, let's say 6% of the quality or asphalt or whatever coverage. They lose 6% of the quality, I'll say, each year. And we need to be smart about this. Your shingles aren't pristine from January 1st to January 30 or to December 31st, and then New Year strikes and they deteriorate by 6% immediately, right? It's a gradual thing. And I would say to people, that would mean that if you had 100% coverage originally, then you're going to have 94% coverage, right? So what I want you to do right now is I want you to figure out what coverage you would have after an additional year. So we need to figure out what we're going to have if we lose 6% of 94. Not 6% of 100, of 6% of 94. And what most Math 20 students do, and what probably most of you or many of you will do, is you will take 94 times 0.06, which is 6% of 94. I hope you're shaking your head, because there's a lot quicker way to do it. And you get this, so now you go 94 minus that, and we get 88.36. And when we do this in Math 20, we're doing this in the context of a common ratio, which, to remind you, is the thing that you multiply regularly by. So the common ratio of a geometric sequence is the base of the exponential function. And then I would say to people, figure out what you multiply 94 by to get 88.36. Well, it's 0.94. And how many of you saw that it was 0.94 to begin with? What you have is whatever you have, you're losing 6% of that. So if you take 100% and subtract 6, that means you're keeping 94%. And what this means in this question is if Allentown is losing 5% per year, the base, which is the factor of change or the common ratio or the thing that the population gets multiplied by yearly, is 0.95. And Brementown is exploding is maybe giving them too much credit. Brementown's population is growing at 9%. That would mean that the base is 1.09. Because it's 100% and you're piling on 9% onto that. So you get 109%, which is 1.09. On a written response on an exam or assignment, you would have to explain where you're getting this from. It's probably obvious to most of us, but you would have to explain it. So that's the answer to the first part of the question, those two functions. The last example here is how many complete years will we have to wait before Brementown's population surpasses Allentown's? I mean, think about it. Allentown starts at 75K and it goes down. Brementown starts at 10K and goes up. They have to pass each other sooner or later. And that would pass, or that would occur when Allentown's population equals, well, we're going to find out where they're equal, and then we'll talk about the passing thing. If we set these two things equal to each other, we would have to solve that for n. And if we got everybody n equals 10.1, we would have to say 11. Because it's complete years. We wouldn't go 10.1 and round it down to 10. We always have to round up in this circumstance. You do not know how to solve this equation, but you will learn how to solve it. So we're going to use our graphing calculator. (75, 1, 2, 3) multiplied by 0.95 raised to the x. You don't really need the brackets around the 0.95. You could just put multiplied by, but I like them. And 10,000 multiplied by 1.09 raised to the x. Help me out here. Did I enter that correctly? I think it looks okay. What are we going to do for window settings? Well, think of our graphs here. I don't think we have to see up to 75,000, but why don't we anyway? Let's go from 0 to 100,000. Now, I'm going to show you a trick here right now. We're going to go from 0 to 100,000. Finding x is kind of complicated, but if you go to your table setup, which is second window, and start at 0, go up by 1 so that it's on automatic, then think about what your table does. Y1 is the population of Allentown after each year. Y2 is the population of Brementown after each year. We don't even need to graph this, do we? Allentown is still more populous. Allentown is still more populous at the end of the 14th year, but at the end of the 15th year, Brementown surpassed it. So the answer is 15 years. When we take a look, close enough. When we take a look here, I'm going to go back to what I had. When we take a look at 14 years, Allentown has more people than Brementown. This is Allentown and this is Brementown. At the end of 15 years, this is 34,747, this is 36. So the answer is 15. Does that make sense? Because I'm seeing a couple of furrowed brows. But you're okay with it, you think? Okay. You know, there might be a case where you want to solve this graphically. I would still look at this table to know that it's going to be someplace between 14 and 15, because then in your window settings, you can say, well, I'm going to go up to 20 because that's going to show me the 14, 15 domain. I said we wanted to go up to 75,000, so I'll stick with that. There's Allentown. People are leaving. Here comes Brementown. People are arriving. Not the same people necessarily. And if you find that point of intersection, if you wanted to know the precise value, you could do that instead. And it's 14.65, so sometime in September maybe, or August, whatever. But if it says after how many complete years, you have to wait till the end of the full year for it to happen. Well, you don't wait till the end of the year, but we want to know how many complete years. If the question said rounded to the nearest tenth, you would just round that number to the nearest tenth. Very general introduction to exponential functions. I guess before we talk about the assignment or the practice, any questions with this? JV? Sure. 0.95 is 100% minus 5% because Allentown is losing 5%. So this is 95%. And of course, percent means over 100. That's literally mathematically what the percent symbol means. It means 95 over 100 or out of 100. And that will give you the 0.95. Whereas Bremen Town, we start off with an initial population of whatever, we're going to call it 100%, and we gain 9%, which is 109%. Does that make sense? And 109% written as a number we can operate with is 1.09. Okay. So on page 342, 3, 4, 6, 8, 10, anything that might, I don't think there's anything, but if you're ever asked to graph, don't worry about graphing it. Jason?
It says 12 in place of...
It says 12 as well on yours?
No, 10 is switched with 12.
So it doesn't say 10, it says 12. Go with what you have. Let me just see what I have here. I've got 10. Go with 12. And you could do both if you wanted to. It's up to you. We don't have a lot of time, but I know you get anxious and you want to look at exams, so I'm going to hand back your exams so you can take a look at them. Some of you are it seems that with written response, you are getting less organized in your work. You want these written responses to be neat, especially with a proof. You don't want to have stuff all over the place, and you want to have a column and another column. It's called two-column proof. Anyway, I'll hand them back, and you can take a look at your work. And I might talk with some of you individually about rewrites today because, as I said, I know some of you are more capable than you might have demonstrated.